This video is about the kinetic model of an ideal gas, which is the basis of the ideal gas law. And first we'll outline the assumptions of this kinetic model. So we're going to write down 5 assumptions here. These are the most important ones. And first we'll just write them down and state what they are. And then we're going to look at a simulation to see what they actually mean. Okay, so the first assumption is that the volume of each molecule is very small compared to the volume of the whole gas. So we could also say that the size of each molecule is much smaller than the distance between molecules. The next assumption is that the molecules are identical spheres and they're all moving in random directions. And the third one is that all collisions, whether it's between 2 molecules or between a molecule and a wall, are perfectly elastic. As you'll hopefully remember from your mechanics topic, elastic collision just means that the momentum as well as the kinetic energy are conserved in the collision. So the total kinetic energy after the collision is the same as the total kinetic energy before. And the fourth assumption is that the duration of collisions is much smaller than the time between collisions. So the molecules are spending most of their time just moving along straight lines, and they're spending a very small amount of time in collisions. Finally, we're assuming that there are no intermolecular forces between the collisions. So the molecules can only feel each other when they're colliding, otherwise there are no forces between them. And this means that there's not going to be any potential energy, it's only going to be kinetic energy. So the energy of these molecules is entirely kinetic. This is the simulation that we're going to use to look at these assumptions in action. So the first assumption, if you remember, was that the volume of each molecule is much smaller than the total volume of the gas. And we can see that in this simulation because I've made it so that there's not that many molecules in here. So we have quite a big box and the molecules are quite small. So the volume of the molecules is smaller than the volume of the gas. Or we can also say that the distance, the diameter of each molecule, is much smaller than the distance between the molecules on average. And the next assumption was that the molecules are identical spheres moving in random directions. Now, in this simulation they are spheres, aren't they? So that's fine. And random directions means that when new particles are introduced, I can add a few new ones. These new particles that were introduced were moving in random directions. And then after that, their direction is going to be determined by the collisions that they undergo. So let's put it back to fewer particles. Okay, the third assumption was that all collisions are perfectly elastic. Now, I guess that's a bit difficult to see here, but it just means that we're not losing kinetic energy as they're colliding. And if we could measure the kinetic energy in here, we would see that the total kinetic energy stays the same in each collision. The fourth assumption was that the duration of the collisions is much smaller than the time between collisions. So if we follow just one molecule around, then we can see that it spends most of its time just flying around and then spends a smaller amount of time colliding. Maybe it's clearer if we use fewer molecules. So now we only have 3 molecules, so we can see them a bit more easily. And we can see that they spend a fair bit of time just flying in straight lines in between colliding. But then they also collide with the walls quite often, but the time that it takes when they're colliding is much less than the time that they're flying in a straight line in between collisions. And then the final and 5th assumption was that there were no intermolecular forces in between the collisions. And that's easy to see here because the particles are moving independently of each other apart from when they're colliding. So they're not attracted to each other. They only collide when their paths cross. The next thing we're going to look at with this kinetic model is the mean kinetic energy of gas molecules. So we know that the gas molecules have kinetic energy because they're moving. And we also know that they have no potential energy because there are no intermolecular forces between them. So what that means is that when we're adding energy to the gas, then that energy goes into increasing the temperature of the gas. Because as you remember, the temperature is a measure of the average kinetic energy. So if we take a brief look back at the phase change diagrams that we did a few videos ago, we can draw a phase change diagram for ice, and then we can try to do the same for an ideal gas and see how they differ. So as we're adding energy to a lump of ice, in the beginning the temperature is going to be increasing, but then we're going to hit the melting point of ice, and beyond that the temperature is not going to be increasing because the ice is now melting. In terms of energy, we're first adding kinetic energy, but then our added energy is going into increasing the potential energy to change the phase of the ice into water. But if we draw the same graph for an ideal gas, it's going to look a bit different, because when we're adding energy to an ideal gas, the only thing the energy can go into is kinetic energy. So all of that energy that we're adding is just increasing the kinetic energy, which is increasing the temperature. So we just get a straight line going up. And from this we can see that the temperature is proportional to the energy that we've added. And because that energy goes into increasing the average kinetic energy of the molecules, we could also say that the temperature is proportional to the average kinetic energy of the molecules in an ideal gas. So that means that we can write an equation to express the average kinetic energy in terms of temperature. And it turns out that the average kinetic energy is 3/2 times Boltzmann's constant, which is in your formula booklet, times the absolute temperature. So remember that the temperature has to be in kelvins for this to work. So armed with this new formula that relates the average kinetic energy to the temperature of the gas, we're going to look at two gases at the same temperature. So we have one box with lighter molecules, which are moving faster, so we draw big arrows, and then we have one box with heavier molecules, which are moving a bit slower. So why are the lighter molecules moving faster than the heavier molecules if they're at the same temperature? Well, if we think about it, the same temperature simply means that they have the same average kinetic energy. And we know from mechanics that kinetic energy is half mv squared, which means that the average kinetic energy is going to be half m times the average value of v squared. So that means that for a larger value of mass, the velocity has to be smaller to give the same value of average kinetic energy. So we can also write this with symbols, so we can say that half mv squared with normal sized letters. If we want to show that the mass is getting bigger, we can just write the m a bit bigger. So we can write half and then a big M, and then we have to put just a small v, which is then squared, because that way our total value is going to be the same as the original half mv squared. So for small mass, we need a higher velocity to get the same kinetic energy, and for a high mass or a large mass, we need a smaller velocity. So that's why lighter molecules are moving much faster than heavier molecules when two gases are at the same temperature. But you might be asking yourself whether these assumptions are really any good. Can we make these assumptions? And isn't it a bit pointless if real gases do not obey these assumptions, if it's only for ideal gases which don't really exist? Well, the answer is that for most purposes, real gases are actually very similar to ideal gases. So the ideal gas law works very well. And when you do experiments, you can see that your calculations using the ideal gas law often give you very good results compared to your experimental results. But we still have to consider this issue, that real gases are not always the same as ideal gases. So we're going to revisit the assumptions that we made. Well, two of the assumptions. The first one was that the volume of each molecule was much smaller than the distance between the molecules. So the problem with this is that real molecules do take up space. And if we have a low density of molecules, then that's not really going to matter. It's only going to be significant at high density, which is also going to mean at high pressure. So let's see what we mean by this. High density is basically how much of the gas you have in a given volume. So we can write that as N over V, where N is number of moles of the gas. The number of moles of gas divided by the volume will tell us about the density of this gas. And the units will be in moles per cubic meter, for example. So what can we say about the pressure then? Well, if we rearrange the PV equals nRT to say that P equals nRT over V, then we can see that the pressure is actually proportional to the density if we're keeping the temperature constant. So if we have a high density, then that also means that we have a high pressure. And another thing that we can tell from this is that it's going to be significant at low temperatures. Because if you imagine a balloon with a gas inside, if we cool it down, the volume of the balloon is going to be decreasing, but the number of moles will stay the same. So that also means that the density will be high. So for a low temperature, we also get a high density, and we said that this assumption was the problem at high density. And the next assumption that we're going to look at is the fact that there's no intermolecular forces between collisions. This one is also a bit problematic, because real molecules do attract each other. They don't just completely ignore each other. And again, this is going to be significant if they're close together, because then they can feel the forces between each other a lot more than when they're far apart. Again, this is going to be an issue at high density. And as we saw above, high density means it's also at high pressure and a low temperature. So these are the three conditions to keep in mind when you're determining whether your gas can be approximated as an ideal gas. So in many everyday cases, we can get very good results using the ideal gas law and assuming that real gases are ideal gases. But under more extreme conditions, we have to use the modified version of PV equals nRT. But this version of the formula is not on the syllabus. So all you have to keep in mind is that the ideal gas assumptions break down for real gases when we have high density, high pressure, or low temperature.